Here we will learn how to balance redox reactions, also known as oxidation-reduction reactions. A redox reaction actually consists of two half reactions. One of them is an oxidation reaction. The other one is a reduction reaction. So those two half reactions combine to give you the full redox reaction. You cannot have one without the other. For every oxidation, there's a reduction, and for every reduction, you have an oxidation. So in these types of reactions, electrons are being transferred. We learned previously in acid-base reactions, it is protons that are being transferred. Protons are being released, and another element takes up the protons. Here, electrons are the ones that are being transferred. An element gives away an electron or electrons, and then another element takes those electron or electrons. So let's talk about an oxidation half reaction. In an oxidation half reaction, we lose electrons, so they are on the product side of the equation. So take, for example, iron plus 2 going to iron plus 3, it loses an electron. So let's take a look at the charges here. On the reactant side, you have a plus 2. And on our product side, we have plus 3 minus, and that's going to be plus 2. So here we are charge balanced as well as mass balanced because we have one iron here and one iron here. A reduction half reaction, remember you cannot have one without the other. Free electrons on the reactant side. Here we gain electrons. So take a look at this complicated half reaction where we have dichromate going to chromium plus 3. So we're going to learn how to do this in this lecture, how to balance it under acidic conditions or basic conditions. So if the problem asks you that to balance this equation under acidic conditions, you can always add H+. On the flip side, if the problem asks you to balance this under basic conditions, you have to balance it with OH-, and we have a problem that could show you how to do that. But let's just take a look here at this half reaction here. Look at the charge here. So we have minus 2 plus 14. Okay, I'm allowed to do H plus because this is under acidic conditions. So minus 2 plus 14 is 12. 12 minus 6 is plus 6. So we have a plus 6 on the reactant side. And 2 times 3 is 6. So we have a plus 6 on the product side. So we are charge balanced. Let's see if we are mass balanced. So 2 Cr here, 2 Cr here, 7 oxygens here, 7 oxygens on the product side, so that's good. 14 H's on the reactant side, 14 H's on the product side. So always make sure you are mass balanced and you are charge balanced. Notice electrons on the reactant side. So here dichromate gained 6 electrons, and in doing so it becomes the product Cr plus 3. Notice above, iron plus 2 loses an electron, and when it loses that electron, it becomes iron plus 3. So basically now all we need to do is cancel out the electrons. It's very important that there are no free electrons in your oxidation reduction reactions. Free electrons are very bad. And so we're going to add these two half reactions and basically cancel out the electrons. We do that by multiplying this top half reaction by 6 in order to cancel out the electrons. Here's a quick review of oxidation numbers. In order to balance these, you're going to need to know how to compute oxidation numbers. This was something we learned in Chemistry 1. Very brief review. There are 6 rules. Rule number 1, standalone elements are equal to 0. Okay, so you don't see a charge here, it's standalone, it's free, that's going to be 0. If there's a charge, the oxidation number takes the charge of the element. So as an example, iron plus 3, the oxidation number of iron is plus 3. O minus 2, the oxidation number of oxygen is minus 2. 99% of the times oxygen will be minus 2. So I want you to remember the oxidation number for oxygen will always be minus 2 in this class. The second rule when it comes to oxidation numbers deals with hydrogen. So hydrogen will always be plus 1. So that is something that you should just memorize. Very rare conditions where hydrogen is not plus 1. But for this course, hydrogen will be plus 1. Standalone elements, as we have established, will have oxidation numbers of 0. But if there's a charge attached to it, as an example, Na+, well, the charge takes the form of the oxidation number. So Na+, sodium ion, will have an oxidation number of +1, as opposed to sodium by itself, which would have an oxidation number of 0. Same thing with the +2 ions that are found in group 2 of the periodic table, and fluorine will always have an oxidation number of -1. Final rule has to do with the rule of addition. So a lot of the ions and substances that we will work with are polyatomic. As an example, the permanganate ion is 1Mn with 4 oxygens, and that whole entity has an overall charge of -1. So the sum of these oxidation numbers will have to equal to the sum of the whole entity. Here the sum of the whole entity is -1. So to figure out the oxidation number, it's going to be Mn and 4 oxygens, because permanganate consists of 1 Mn and 4 oxygens, with an overall charge of the entire polyatomic ion being -1. So we know that oxygen will have an oxidation number of -2. Remember, 99% of the time oxygen will have a charge of -2. So doing that math here, 4 times -2 is -8. We'll take it to the other side. So -1 plus 8 is +7. In the permanganate ion, MnO4-, manganese has a charge of +7. So let's do a problem here where we're asked to balance this redox reaction under acidic conditions. So first and foremost, 2 things about balancing a problem under acid. So the first thing is that we have 2 of a lot of things. We have a lot of water, because you see this redox reaction is occurring, the transfer of electrons are occurring in the solvent of water. So we have a lot of water around, so we can use that to balance our redox reaction. And another thing that we could do, second thing we have in abundance is protons H+, right? So H+ is around that we can use to balance this, as well as water. Why protons that are in abundance? Because this redox reaction is happening. They tell us it's happening under acidic conditions. If they tell you it's happening under basic conditions, you will balance it with OH-. So the first step is to calculate the oxidation numbers. So doing the oxidation number rules, where rule of addition, we have 2Cr plus 7O. All of that has to equal to -2. Oxygen is going to be have an oxidation number of -2. So doing that math, I have Cr chromium in dichromate. This is the dichromate ion. Has an oxidation number of +6. Cl takes the charge of -1, so here the oxidation number is -1. Going to the product side, Cr by itself is going to have an oxidation number of +3. Notice the charge takes the oxidation number. And then Cl2 is standalone by itself, and that has an oxidation number of 0. So look what's happening here in step 1 when we initially formulate the oxidation numbers. We have chromium going from +6 down to +3 in oxidation state. It's going down. On the flip side, Cl, or chlorine, is going up from a -1 oxidation state to a 0 oxidation state. So one is going up, one's going down. Redox reaction for a reoxidation, there's a reduction. All right, so step 2 is we're going to balance these half reactions. So let's first do the dichromate going to Cr plus 3. That is our first half reaction. Our second half reaction is Cl minus going to Cl2. All right, so the first thing we want to do here is balance all of the atoms that are not hydrogen or oxygen. And for me, that's going to be the chromium. So notice here we have 2 chromium on the reactant side. So let's balance the chromium. Problem here in this half reaction, again, we're splitting this full reaction into half reactions. Then we'll recombine them together, these half reactions, canceling out the electrons. And that will give us the balanced oxidation reduction reactions. So we balance the chromiums. How will we balance the oxygen? Okay, again, these are all happening in water. So we'll balance the oxygen with water, so it's implicit that water is there. So 7 oxygens here, so that's going to be 7 H2Os on the product side. So let's go ahead and put 7 H2Os on the product side. So we balance the oxygens. Now we have hydrogens. So how will we balance the 14 hydrogens on the product side? Again, acidic solution, that's a big hint. We can balance the hydrogens with H+. So I'm going to put 14 H+ on our reactant side to balance out the hydrogens. All right, so it seems like everything is balanced. The only thing that's left is the charge. So minus 2 plus 14. So minus 2 plus 14 is 12. And here we have, on the product side, plus 6. So how will we balance this out? To me, to balance this out with free electrons, we will need 14 minus 2 is 12. 12 plus 6e minus would give you plus 6. So let's balance this by putting 6 electrons on the reactant side. This is a reduction half reaction. So this is reduction because the 6 electrons are on the reactant side. Let's just do a double check and make sure everything is okay. Let's first do the charge. Minus 2 plus 14 is 12. 12 minus 6 is plus 6. 2 times 3 on the product side is plus 6. We are charge balanced. This is a 6 electron transfer reaction where Cr2O7 gains 6 electrons, and in doing so it becomes Cr plus 3. Atoms 2Cr and 2Cr balanced on the reactant and product side, 14 H's, 14 H's on the product and reactant side, and 7 oxygens on the reactant side, 7 oxygens on the product side. So this half reaction is balanced. Furthermore, it is a reduction half reaction. Gain of electrons, reduction. Electrons are being on the reactant side, so this is a reduction half reaction. Our next step is to balance the remaining half reaction, which obviously has to be oxidation. See, if this is reduction, then obviously Cl going to Cl2 is going to be the opposite, which is oxidation. So let's go ahead and balance that. So here's our second half reaction. First thing we'll do is we'll balance the chlorines. Okay, so I'll put a 2 there, and that balances that. And I think that's it. The only thing left is to balance the charge. So there's no oxygen that we need to balance with water because we have plenty of water around. And there's no hydrogens that we need to balance with H pluses because this is an acidic solution. So what do we need to balance this? Minus 2 on the reactant side, and to get to minus 2 on the product side, we need 2 electrons, 2e. All right, so this will be an oxidation half reaction shown here below the second half reaction. Minus 2 on the product side, minus 2 on the reactant side, that's good. 2Cl on the reactant side, 2Cl atoms on the product side, we are balanced. So this is the reduction above, this is the oxidation at the bottom. We need to join them together and cancel out the electrons. Very important, no free electrons in your final answer that you report. To do that, all we need to do is just really multiply this bottom half reaction by 3 to get 6 electrons that will cancel out. So step 3 is to cancel out the electrons, and in this specific problem, we do that by multiplying the second half reaction by 3. So multiplying the second half reaction by 3 gives us 6Cl minus goes to 3Cl2 plus 6 electrons. So it's very important that these 6 electrons on the product side will cancel out with these 6 electrons on the reactant side of this reduction half reaction. So what we're left with is our final answer, and let's check to see if everything is balanced. This is the final answer that I'm getting after we cancel out the electrons. Cr2O7 plus 14H plus 6Cl minus is going to go to 3Cl2 plus 2Cr plus 3 plus 7 waters. Let's do a double check to make sure that this is indeed mass balanced and charge balanced. Let's first do the charge. So minus 2 plus 14 is plus 12. 12 minus 6 is plus 6. 2 times 3 is plus 6 on the product side, so everything is fine there. Um, let's see the atoms, 2Cr, 2Cr balanced, 14 H's, 14 H's are balanced, 7 oxygens and 7 oxygens are balanced, both in the reactant side and the plus product side. And hydrogens are balanced, 14 each. Chlorines, 6Cl, chlorines on the reactant side, 6Cl, chlorines on the product side. I think this is balanced, mass balanced, and charge balanced. This is the final answer to how to balance this equation under acidic conditions. So under acid conditions, dichromate gains 6 electrons, and in doing so, it becomes Cr plus 3. And also Cl minus gives up 2 electrons, and in doing so, it becomes Cl2. Okay, so that is the electron transfer that's going on. We had to do some balancing to get our final balanced redox reaction. So let's do our second problem here. This one is different than the first one in that we're balancing this under basic conditions, which means that two things. One, like before, we have a lot of water around, which is fine because all of this is happening in water. But contrary to the first equation that we balanced, this is in base, so there's going to be a lot of OH minus, a lot of hydroxide. So we're going to balance it with hydroxide. So first thing is calculate the oxidation numbers. We have MnO4 minus going to MnO2. Oxygen will always be -2, so that's not a problem. It is Mn that we're concerning ourselves with. So Mn plus 4 oxygens, all of that has to equal to -1. Manganese, we will have an oxidation number of +7 here. And in the product side, MnO2, we have Mn plus 2 oxygens going to 0. The total charge here is 0. And Mn will be +4. So we're going from +7 down to +4. Let's look at the bromine now. Br minus, remember the charge takes the oxidation number. So bromine here in the reactant side will have an oxidation number of -1. And BrO3 minus, this is called bromate. Bromate ion, BrO3 minus. So BrO3 minus, the oxidation number here of bromine is +5. So -1 for bromine in the reactant side. The oxidation number on the product side for bromine goes up to +5. So we're going down in oxidation number in one and up in oxidation number in the other one. This is a perfect example of a redox reaction. So let's first do our first half reaction. MnO4 minus goes to MnO2. First thing that we want to do here is, well, the Mn and Mn are balanced at 1 apiece, so that's fine. So what we want to do here is balance the oxygens. So let's balance the oxygens with OH because we are in basic solution. So I think that should be all right. So I'm going to balance this with 2 hydroxide ions. And I'm going to put that on the product side. All right, so my 2 hydroxide ions will balance out the oxygens. Now I have 4 oxygens on both my product side and reactant side. 2 plus 2 is 4. So what do I need to do to balance the hydrogens? Well, I'm going to balance the hydrogens not with water. I'm going to balance the hydrogens with H+. Now you may think that that is a wrong idea because this is in basic solution, but we can neutralize that later on. So technically what I'm doing now is not right, but we'll make it right later on. Okay, so we can't balance this hydrogens with water because that will create an imbalance with our oxygens. The oxygens will get messed up. We can balance the hydrogens here on our product side with H+, and then remedy that later because knowing we are in basic solution. So I'm going to balance the hydrogens by putting 2 H+ on the reactant side. So let's go ahead and do that. All right, so now I have 2 H+ here. Technically, cannot do that because there's a lot of base around and not a lot of acid. But because there's a lot of base around, I can also neutralize this H+ with OH-. So that's how we remedy this situation. I'm going to add 2 OH- here to balance out the H pluses. So 2 OH-, and whatever I do on the reactant side, I'm going to do on the product side. So to neutralize the 2H+, I'll add 2 OH- on the reactant side, And because, again, whatever I do on the reactant, I must do on the product. On the other side here, I'm going to add another 2OH minus. So here I'm going to put step 2A for this first half reaction, neutralize out the 2H pluses with 2OH minuses. And because I put 2OH minuses on the front side, I got to put 2OH minuses on the back side of the reaction. So, or the product side of the reaction. So the key here is that the 2H plus and the 2OH minus, remember I'm in basic solution, so there's a lot of this around. The 2H plus and the 2OH minus is nothing more than 2 waters. Okay, so this is nothing more than 2 waters. And on the product side, 2OH minus plus 2OH minus becomes 4OH minus. So let's go ahead and do that and sort of clean this half reaction up, which is kind of messy. All right, so the difference between the top and the bottom is that I added the OH minus to get 4OH minus, neutralized out the H plus with OH minus to give you 2 waters. And now let's just check to make sure that we are all balanced in terms of atoms. So 4 H's, 4 H's, 4 oxygens, 2 plus 4 oxygens is, 2 oxygens plus 4 oxygens is 6. 2 oxygens plus 4 oxygen is 6. So we are balanced 1 Mn and 1 Mn. So all we need to do now is just balance it out with electrons. So we have -1 on the reactant side. Here we have -4 on the product side. So I think what we need to do is we need to add 3 electrons on the reactant side to get us balanced in terms of charge. So I'm going to add 3 electrons here on the reactant. All right, so once again, -1 plus -3 is -4. This is a -4. This is a reduction half reaction. It's a reduction half reaction because MnO4 minus gained 3 electrons, and in gaining 3 electrons, it has become MnO2. Well, we got to do one more half reaction, and that's going to be Br going to BrO3 minus. So let's go ahead and do that under base. All right, so here's our second half reaction. Br minus going to BrO3 minus. So just making sure I copied this right. I did. So Br minus going to BrO3 minus. So the Brs are balanced. So let's go ahead and balance the oxygens with hydroxide ion. Okay, not water, but hydroxide. And that's going to be 3 OH minuses on the reactant. All right, so 3 OH minuses on the reactant side. Let's balance the hydrogens with H plus, realizing that we will rectify that issue later. So we'll put 3 H plus here on the product side. So now we have 3 H pluses here. We are in base, so let's neutralize the H plus with 3 hydroxide ions. And whatever we do to one side of the equation, we have to do to the other. So we're going to add 3 hydroxide ions to both sides of the equation to neutralize the H plus that's on the products. So the OH minuses that I've added for neutralization of the H plus, which I added to balance out the hydrogens, that's shown in purple. Again, whatever we do to one side of the reaction, we have to do to the other. So this H plus plus OH minus becomes 3H2O, and this becomes 6OH minus. All right, so I'll highlight that H2O in purple because that came from neutralization, and we got 6OH minus from above. So now let's just do a quick inventory here. 6 oxygens and 3 plus 3 is 6 oxygens. Br1, Br1, so that's balanced. 6 hydrogens, and 3 times 2 is 6 hydrogens. So I think we're all good. All we need to do now is balance things out with electrons. So we have -6 plus a -7. So that's, -6 plus a -1 is a total of -7. Here we have a -1 here. So what do we need to do to balance out the electrons? I believe we need to put 6 electrons on the product side. So if I put 6 electrons on the product side, we are charged. So I highlighted the electrons that are being transferred in red. So let's just go over the charge one more time. So -6 minus 1 is -7. -1 plus a -6 is -7. So we are balanced charge and mass-wise. Mass and charge balanced. So this is going to be an oxidation reaction. Okay, so how do I know it's an oxidation reaction? because Br minus to become BrO3 minus has to lose 6 electrons. Okay, let's highlight our reduction reaction in also yellow. MnO4 minus gains 3 electrons to become MnO2. So here's our reduction, here's our oxidation. Let's add them up together and canceling out the electrons. So I see automatically if I add or multiply this top reaction by 2, this top half reaction by 2, I'm able to cancel out the electrons. So let's do that and then get our final answer. All right, so we're going to multiply in our last step, canceling out the free electrons. Here is our both our half reactions. One's reduction, one's oxidation. We're going to multiply the top one by 2 and to get rid of and cancel out the electrons. So 2 times 2H2O is 4 times 2MnO4 times 6 electrons goes to 2MnO2 plus 8 OH minus. We're going to leave the second half reaction alone. And one thing you'll notice here, the most important part of this step, is that the 6 electrons on the reactant side of this half reaction will cancel out with the 6 electrons on the product side of the other half reaction, and we should get our final answer. And make sure at the end it's mass balanced and charge balanced. Before we do that, I do want to tell you something here. Notice very carefully, this OH, the 8 OH minus on the product side cancels out with 6 of the OH minuses on the reactant side, so we're actually left with 2 OH minus. And let's look at the water here. The 3H2O here on the product side will cancel with the 3 H2Os here on the reactant side, leaving us with remaining 1 water molecule. So if you want to cancel anything that you can cancel, 3 waters cancel that with this, leaving you with 1, and 6 OH minuses cancel out with this, leaving you 2. So now we have our final answer. Let's tally everything up and make sure we are mass balanced and charge balanced. All right, so here's our final answer. Let's just do an inventory here. We got Br minus plus water plus 2MnO4 minus in our reactant side. That's going to go to 2MnO2 here, plus BrO3 minus on the product side here, plus 2OH minus on the product side there. So let's cross our fingers and hope everything is balanced. So 1 Br and 1 Br are balanced. 2 H's and 2 H's are balanced. Very good. So O plus 4O here is 5O. 3O plus 2O here. So O here plus 2 times 4 is 8. 8 plus 1O is 9. 3O plus 4O is 7. 7 plus 2O is 9. 2Mn and 2Mn. So I think we're all balanced. Let's check the charge. -1 plus -2 is -3. And -1 here plus a -2 is -3. So we are mass balanced. Yes, we are charge balanced. And this is the right answer for our redox reaction under basic conditions.